In the previous lecture, we learned about the state space representation of mechanical electrical systems. Then we moved forward talking about the transfer function conversion into state models, and then given a state model, converted back to transfer function. So today we'll talk about an important concept related to state space analysis called as controllability and observability. So these concepts were given by a person named Coleman. So these concepts are very important in the design of control systems in a state space. So the conditions of controllability and observability may govern the existence of a complete solution to the control system design problem, which means that you will be able to design the control systems if you observe that the systems are controllable and observable. And what is controllability? So a system is said to be controllable at the time t naught if it is possible by means of an unconstrained control vector to transfer the system from an initial state x t naught to any other state in a finite interval of time. So this is how we define controllability. So in other terms, we can say that the question of controllability is that can we control all the states of the system through the input channels we have? So if you look at the general definition, the main definition of controllability, it says that the system is said to be controllable at time t naught. T naught stands for the initial time. If it is possible by means of an unconstrained control vector. So here, unconstrained control vector talks about the input that you are going to provide to the system. So this input may be a single input or multiple inputs. So thus if you have multiple inputs, it will be forming control vector unconstrained, that there is no limit on the input that will be provided to the system. And application of this input, if it is going to transfer the system from an initial state x t naught. So since initial time is t naught, the initial state would be x t naught. And if this input is going to transfer the system to any other state in finite duration of time. So if you're going to have system states initially as xt naught, so if the initial states is xt naught, and on application of an input u, let's say an unconstrained input control vector u, if this state is going to be transferred to another state after a duration of time, finite time t, let's say t1. So if you are capable of doing so, then your system is said to be controllable. I repeat, if you go if on application of a control input u, if you transfer your system states x from an initial state xt naught to a final state xt1 within a finite duration of time. So t1 defines that duration of time. Then your system is said to be controllable. So if we talk about the example given below, which comprises of two masses m1 and m2 connected together, and then you have a single input applied to mass m1. You could have multiple inputs like f1 and f2 at other location, or any other sort of input given to this system. So if suppose that on application of the input f, now in this system you have state variables like the displacement in mass m1, the displacement in mass m2, and their velocities. So if the state variables, the identified state variables for this system, if let's say they are 4, the displacement of the two masses and their velocities, that accounts to 4 state variables. So in an application of the input f, if all these 4 state variables are going to take a finite another are going to change or going to transfer to another state variables within finite duration of time, so then this system is said to be controllable. In other words, if by application of a suitable input f, if you attain a desired state within a finite time, desired state means that the state that you were expecting to uh, happen to occur after a certain time period by application of a known input or by application of a suitable input, then you say that the system is controllable. Now, if you consider that the system is given by these expressions, so this is nothing but the state space representation of any system you already studied. So this system is said to be state controllable at t naught if it is possible by means of an unconstrained control vector to transfer the system from any initial state xt naught to any other state in a finite interval of time t naught t lying between t naught and t1. So this is the same definition that we discussed in the previous slide. Mathematically, if you want to know whether the system is controllable or not, so we have an expression. If this expression uh, is going to meet the requirement for the system to be state controllable, then we say that it is controllable. So we are talking about state controllability. So this is a slight change that is observed, that and controllability can be talked in terms of two terms. One is called as the state controllability, the other is the output controllability. So a system is said to be state controllable if if within a finite duration of time from t naught to t1 from t naught to t1, if on application of input u, you're going to have you're going to transfer the state from an initial state xt naught to a final state xt1, then it is said to be state control. And this mathematically, for system to be state controllable, it is necessary that the matrix called as controllability matrix, which is given as qc, equal to b a square b and up till a to the power n minus 1 b has a rank of n. So n is the order of the system, which can be judged through the. So I'll talk about this later when I do example. So how are you going to talk about n? So if QC given by this expression, which or this matrix which accompanies these terms, if it has a rank of n, then the system is said to be controllable. So this is the way we check the controllability of a system mathematically. So this becomes the qualitative definition. Sorry, quantitative definition. While the definition that was given previously is a qualitative one. Now, if you talk about the output controllability, that is the second type of controllability. And what does the definition for this, or the qualitative definition for this is? So you can define this as that the system is said to be output controllable at t naught if it is possible by means of an unconstrained control vector to transfer the system from any initial output yt naught. In case of output controllability, you will have here a yt naught term to any other state in a finite interrupt to any other output. So you're going to transfer y from yt naught to yt1 within a finite duration of time by application of a input. Then you say that the system is output controllable. So mathematically, if this is given by a term QC equal to CB, CAB, C square AB, and CA and to the power n minus 1B, if it has a rank of n, then it is said to be output controllable. And rank of n means that the matrix is a non-singular matrix. So we'll talk about what is singular and non-singular matrix in brief. Now, the other definition is observability. The system is said to be observable at time t naught if it is possible to determine the initial state x t naught from the observation of the output over finite time interval. Or the question of observability is that the is that can we, so this should be, this should not be here. The question of observability is that can we determine all the states of the system by observation of the sensors we have. So the term observability, or we say that the system is observable at time t naught if it is possible to determine all the initial states, or if it is possible to predict the initial states x t naught. So it means that if suppose that you're given a system and you didn't knew about the states that existed at time t naught. Let's say you were operating the system at time t1. So at time t1 the states would have changed to xt1, and let's say it was having a certain output yt1. So if by observation of this output which was attained in a finite time t1, so the system is said to be observable if you can predict the initial states xt0 using the output yt1 attained within finite time interval, then we say that the system is observable. So you're doing some sort of prediction here. The question of observability is that can we determine all the states of the system by observation of the sensor. Sensors means that you will be sensing or you will be measuring the outputs y using sensors. So this is what it means. So are you able to determine all the states at t naught of the system by looking at the output y? So we have consider the system. Consider a system described by these equations. So again, the state space representation of the system. Now, for an unforced system means that you are not going to provide any input. So since if you look at this definition, we didn't talk about input anywhere, and we only talked about the output y, the initial state x. So we are going to try we are trying to find the relation between y and x uh, in order to come up with an expression that defines observability. So that is why we choose to have u equal to 0. So that makes it an unforced system. So unforced simply means that you are not going to provide any input to the system. So here u becomes 0. Now you're left with an equation, a state change equal to ax and output equal to cx. Now this system is said to be observable if every state xt naught can be determined. So this is an important condition, that you must be able to observe, or you must be able to estimate every state xt naught. It's not like if you had 4 state variables within the system and you were able to predict only 3 of them or 2 of them. So if you're not able to predict all the state variables present in the system, then we don't say that the system will be observable. So the important condition is that the system is said if every state xt naught can be determined from the observation of y over a finite time interval. Every transition of the state eventually affects every element of the output vector. So from the definition, it means that if you're going to have a change in the state, every state. So if you talk about 4 state, for example, the example that we talked about in the first slide of 2 masses connected together, it had 4 state variables. So if the 4 state variables are going to change, then this will be affecting the all the outputs present in the system. So any output that you talk about within the system will be affected by change in the state variables. For example, the same example of 2 masses, you have 2 output. You may be having 2 outputs in the form of displacement of the 2 masses. So it means that all the 4 variables, the displacements of the 2 masses and the velocities will have to affect the output of the uh, 2 masses, which is displacements of the 2 masses. Then we say that the system is satisfying the condition of observability. So, this concept is useful in solving the problem of reconstructing unmeasurable state variables from measurable variables in the minimum possible length of time. So, you might in future come across things called as uh, state feedback control. So, this is part of control using a state space. The concept of state space, we call it as state feedback control, where the state variables from within the system are all the state variables from the system are being measured and then fed back to be compared with a certain reference state variables. And this is how we accomplish the control systems, by measuring the state variables. State variables have something that are from inside the system. They are not always the output of the system. So we are designating state variables by X while the output is designated by Y. So in state feedback control systems, what we do is we measure all the state variables in order to in order to provide control to the system. So this is what it is mentioned here. So it's useful in solving the problem of reconstructing unmeasurable state variables. So in such problems, if you have state variables that cannot be measured by any means, let's say you had four variables, and out of these four state variables in the system, you have sensors that can only measure three variables, and the fourth variable, which was required to be measured, doesn't have any sensor, or it was by some means could not it by some means cannot be measured. In that case, you will be estimating that particular variable, which is unmeasurable, using the measurable variables. So that could be output. So using the output, if you are able to estimate the unmeasurable state variable in a finite duration of time, then this can only be possible if the system is observable. Mathematically, we define the system to be observable. To be state observable, it is necessary and sufficient that the observability matrix given by. So I guess state observable doesn't have any sense. So you shouldn't be writing state here. So system is simply observable, because in controllability we had two concepts like state controllability and output controllability, but it doesn't hold here. So for the system to be observable, it is necessary and sufficient that the observability matrix, which is given as Q naught equal to C CA square up to CA to the power n minus 1, should have a rank of n. Again, this should be a non-singular matrix. So just for a quick recap, for a controllability matrix, you should have this matrix given by QC equal to B A square B up to A to the power n minus 1 B should have rank of n. And the observability matrix, which differs from this matrix in the sense, so you have the elements in this matrix. The first element is A, starting from the second column, and the power of A keeps on increasing. While in case of controllability matrix, you have first of all the matrix given in the transpose form of QC, the controllability matrix. So you have a column matrix here, and instead of taking the first element as A from starting from second row, you are going to take the element A as the second element, and going to increase the power of A in the similar manner. So this is a slight difference between the two matrices. So let's try to do examples based on these. So given here is a question says that examine the state controllability of a system given by. So in this particular question, you are required to only examine the state. You are required to only check whether the system is state controllable. So this is the equation that is given in the form of x dot equal to ax plus bu. So this becomes matrix A and this becomes B. Now in order to check whether the system is state controllable, you will be using the same definition that we have. So the controllability matrix, which is A square B up to A to the power n minus 1 B, should have a rank of n. So in order to do this, so you have B. So how are you going to judge the power of A? to what maximum power of n, or what maximum value of n are you going to choose in this expression. So you could have written here as b a b a square b. Why have you written b a b? So any answer from your side? How do you choose the power of n here? I repeat the question. I've written QC as b a b and not written a square b, because I say that n here is taken as 2. So why are you taking, from where have you taken n as 2? So in the previous slides, I told you that n is the order of the system. So how did you identify the order of the system in this case? Anyone? Which one is it? 2 cross 2 matrix. From which matrix are you going to say that n is 2? I said that you are going to choose the value of n as 2 in this case, because so I told you in previous few lectures, I don't exactly remember which lecture, but I told you that the order of the system is decided by the order of the matrix A is decided by the order of the system. So if you have a order 3 system, in that case the size of matrix A would be 3 cross 3. So since you have a matrix with a size of 2 cross 2, which means that the system order is 2. So that is why we are going to take the value of n as 2 here. So if you see that n is written as a at it, the maximum value, the maximum power of a should be n minus 1. And since in the present question you have n is equal to 2, and then you are going to put 2 here, you get 2 minus 1 as 1. And that is why we have taken the maximum uh, term as a to the power 2 minus 1, which is ab. All right. So you identified this system to be a second order system, and that is why you place the terms like b a b and not a square b. And since b is given as 1 0, so you're going to substitute 1 0 here. You get this term. So this is b, and ab is the multiplication of matrix A and B. So if you're going to multiply these two matrices A and B, then what you get is 1 0. So this is the multiplication of A and B. So you can verify this from the matrix 1 1 multiplied by 1 0 gives you 1, 0 minus 1 multiplied by 1 0 gives you 0. So this becomes 1 0. So since this matrix is singular, the system is not state controllable. So the condition for state controllability is that the matrix given by QC should be non-singular. So how do you identify that the system is singular? So how do you identify that this matrix is singular? What is singular matrix or a non-singular matrix? So to identify a system being singular or non-singular, you'll check the determinant. So in this matrix, you have determinant as 0, and hence this becomes a singular matrix. So to know whether the system, to know whether the matrix is going to have a rank n, you will have to check the determinant. So since this is a 2 cross 2 matrix, the determinant for this matrix is 0. Determinant for this is 0, and hence this becomes a singular matrix, and the system is not completely state controllable. The condition for being state controllable was it should have rank of n, where n was the order of the system. And since the order of the system is 2, and you found that this matrix QC is singular, or it is having determinant 0, and thus it does not have rank of 2, and thus it makes the system uncontrollable. Now if we have another example, we want to examine the state controllability of the system again. So there's only slight change in the input, I think, as well as the matrix A. So for this case, you have QC given as B, A, B. Again, this is a 2 cross 2 matrix, and hence the order of this system is 2. And that is why you're going to take two terms only, B and AB. And if you evaluate this, you get the determinant of this matrix is not 0. So minus 1 multiplied by 0 and 1 multiplied by 1 gives you minus 1. Since the determinant is not 0, this becomes a non-singular matrix and the system is completely state controllable. So in order to know whether the system is controllable or not, you will be evaluating the matrix QC, the determinant of matrix QC. If this determinant comes out to be 0, then the rank will not be equal to its order and hence the system will not be controllable. If QC, the determinant of QC comes out to be non-zero, in that case the rank is going to be equal to the order of the system and hence the system will be completely state controllable. Now we have another example. Examine the controllability and observability of a system given by. Now since you are not written here, it's not written here that find the state controllability. So they have written it generalized form controllability, which means that we'll be finding state controllability and output controllability as well. So suppose you're given the system by the state equations and output equation. So you're desired to find controllability and observability of the system. So we start with QC. So the rank of QC, which is nothing but the matrix accompanying the matrix P and multiplication of AB, and this gives you QC as 0, 1 and 1 minus 1. So the rank, if you find the determinant of this matrix QC, this is non-zero. Determinant comes out to be non-zero and hence the rank will be equal to 2. Thus the system is completely state controllable. Now if you talk about the output controllability. So in case of output controllability, you are going to use the matrix this one. So CB, CAB, CA square B and so on. So again you will be having, because n is equal to 2, and thus you will be having CB and CAB only. Now if you evaluate this matrix QC using C is 1, 0, A is this, B is this. So if you're going to substitute these matrices in place of C, B and A, what you get QC is as 0 and 1. So the rank of this matrix is 1. Now there's a slight change in the definition that QC has a different order from Q, the order of this system. So, and it has a matrix, it has a rank of 1. 1 is because you are having one element which is non-zero, or a 1 cross 1 matrix within this matrix comes out to be non-zero and hence its rank is 1. So the system is said to be output controllable. So I guess there's a slight confusion here. So I'll make this clear later on. No problem. So main thing is that you stress on state controllability and output of the observability of the system. Now, if you suppose you're asked the question to examine the observability of the system given by x dot equal to ax plus bu and y is equal to cx, and given is the x equal to x1, x2, x3. So this has three state variables. Then you have matrix A, B, C given as follows. Now to obtain the to know the observability of the system, you are required to construct a matrix Q naught, which was given by C, CA, CA square, and now C is given as 451. So you substitute it again. So, okay, this should have been a transpose here. So if you're going to So since Q naught is given by C, CA square, if you're going to place C, then in that case, what you get in the form of matrix is 4, 5, 1. Then you're going to evaluate CA. So you're going to multiply C with this matrix. What you get is minus 6, minus 7, minus 1. Then again, if you're going to multiply CA with A matrix again, then in that case you get this as 6, 5, minus 1. So I should have written this matrix here, but I have written transpose, and nevertheless you take the transpose of this matrix to get the same matrix, this matrix. Now if you're going to compute the determinant of Q naught, so this is going to be 0. So determinant of this matrix will be equal to determinant of this matrix. So it's not, there's no difference in the determinant of the two. So you take the transpose, you get the same determinant. So if determinant of Q naught is going to be 0, then the rank of this matrix is less than 3, and thus the system is not completely observable. So this is how you're going to solve the problems, by mathematically using the expressions corresponding to controllability and observability. And in case if determinant of QC or Q naught are going to be 0, then in that case you will be having a rank less than the order of the system, and thus the system will not be controllable and observable. But in case any of these comes out to be equal to the order of the system, let's say QC was equal to the order of the system, then we say that the system is controllable. And if Q naught also comes out, the rank of Q naught also comes out to be equal to the order of the system, then we say that the system is observable. There is a note written: if a system is completely state controllable and completely observable, its transfer function will have no cancellation. So what does this mean? So suppose that you have a system which was completely controllable and observable, and you represented the system into transfer function form, which means that let's take an example. We had the transfer function representation of a system, and let's say we got the transfer function as s plus 1, s plus 2 divided by s plus 3 and s plus 1. So let's say this was the transfer function of an arbitrary system, which was, so the condition for it to be completely state controllable and observable is that there should be no cancellation. Cancellation means if you look at this term s plus 1, this gets cancelled by the s plus 1 in the denominator. So we observe a cancellation. This is also called as pole zero cancellation, which we'll be discussing later units. So if you observe any sort of cancellation in the transfer function, then the system will not be state controllable or observable. If cancellations are not existing, then it may be possible that the system is controllable and observable, which will require further uh, checking with using the concepts that we studied. So I guess this makes clear things, and if you have any doubt, any problem, you can ask me questions.